Hello everybody. In this video I'm going to be talking about sampling and discrete signal processing. So sampling is a really important tool that we need because a lot of real life signals such as audio recordings and voltage measurements are analog and they're continuous signals, so they're not really feasible to work with in terms of computing, and we want to leverage the power of computers to process these signals. But in order to allow computers to deal with such signals, we need to make them discrete. We need to give the computer a finite list of values, and sampling is the way that we do that. We take a continuous time signal and we turn it into a discrete signal, and now the computer is able to make computations on it. And oftentimes what we'll want to do is we'll want to give that to the computer, process it, and then turn it back into some continuous time signal. So today we're going to talk about that. We're going to answer these two questions. First, how do we sample and reconstruct continuous signals? And then two, I'm going to cover this in the next video, but in the same notes, under what conditions can we perfectly reconstruct the signal? So let's just go through this step by step. Let's just start with some continuous time signal x of t, as shown in the diagram here. It's just some smooth continuous function. We can utilize the sifting property of the delta function to sample values from this continuous function x of t. The sampling function that we're going to use is the impulse train, as it's called. We're going to call it I of t. And we have some control over this impulse train, mainly the sampling period is what we're going to call it. It's essentially the spacing between these impulses, these unit impulse functions. And as we'll see later on in this, when we talk about the sampling theorem, this is going to be a very important parameter to keep track of. Equivalently, we can think about this as a sampling frequency, which we'll also talk about. And I of t is just given by this infinite sum of delta functions spaced out at integer multiples of this sampling frequency. So to sample our function, this is just the sampling function, but in order to actually sample the function, we can multiply our continuous time signal by this impulse train and sum them up. So it's going to look something like here in figure 2, where we have this curve that looks like this. It has this general shape. And then when we multiply it by the impulse train, what's going to happen is that the impulse train is going to simply just pick out these values from this function. It's going to sample them, and it's going to kind of create this general shape with all those impulses that are the same spacing, but now they're just scaled by whatever value they had at that point, right? So this is the idea of sampling. So now we're going to take a little bit of a leap of faith here, but I promise it'll all make sense if we go through all this. So as we can see from x of p, which is what we're calling our sampled discrete function, is the sum of these impulse scaled by the function at integer multiples of the sampling frequency, or sampling period t of s. At this point, we have converted the signal into a digital signal where we can process it in a manageable way. Since now we have a discrete set of values that the computer can handle. Now, this is where we're going to take a little bit of a leap of faith, and then we're going to circle back to make sure we understand this. The last step is to convert it back into an analog signal. So at this point, we already have something that the computer could work with, and maybe we do some stuff to the signal, but now we're going to want to convert it back into a analog continuous signal. So what we're going to do is we're going to multiply this discrete x of p of t signal by an interpolating function, which basically takes our discrete function and kind of connects the dots in some way, right? And this is maybe out of left field, but the interpolating function we typically use is this sinc function, which has this interesting shape. And this may feel out of left field, but the thing is that we can't really understand this without looking at the frequency domain process that we just did. This is a block diagram showing we just did, right? We have our continuous signal x of t, and we generate x of p of t by multiplying it by the impulse train. And then we're going to do this thing called interpolation, which is essentially connecting the dots. And then we get our x of r, which is what we're calling our reconstructed signal. And we're going to come back to this interpolation idea after we do the sampling theorem and after we look at this block diagram, but in the frequency domain. All right, so just to review, the sampling can be done by multiplying our signal by an impulse train of period Ts. This gives us x of p of t, which we can process easily. Then to reconstruct the signal into the x of r of t, we can multiply it by interpolation function. Now, we have answered the first question. We now know how we sample and reconstruct a signal in the most basic sense. But now let's look at the more interesting question. When is our reconstructed signal xr of t equal to the original function x of t? In other words, when is the reconstructed signal equal to the original signal? In the next section, we'll discuss some of intuition as to why they're not always equal, and then we will analyze the process in the frequency domain to better understand the conditions necessary to perfectly reconstruct a signal. And we'll be going over that in the next video.